Octavio, can you hear me? Sorry, Octavio, can you hear me? Se riesci. Ottavio, mi puoi sentire? Perché ho cambiato, ho cambiato ho fatto un'altra videoconferenza. Ho-
Sì,
tranquillo,
sentiamo.
tranquillo. Ok. Sì, sì, scusa. Sì? Sì? Però mi stai chiedendo, diciamo, la mia identità. Ma deve avere un account su GitHub. Deve avere un account su GitHub per poter fare il pool. Sì. Non l'ha mai fatto prima? Ah no? Ma adesso sono diventati noiosi quelli di GitHub. Strano. Ehm, Cominciano a cambiare le regole, vogliono fare darla a tutti, diciamo. La prova non ha dato problemi, no? No, no, qui non ha... Strano, la prova non le ha dato problemi. Allora, lei però non ha deciso neanche le sue dati. Napolino no. No, no, però dico le cose... Cioè, non penso che posso fare su cui finisce, perché qui è... Qui è un account, cioè la repository, e questi sono i commit. Questa è l'iconcina, no? Sì, sì. Ah sì? Sì. Eh,
Ho giocato tutta machine, non sto dato un po' di foto. Adesso facciamo le prese con dietro. E ha delle cose che aveva lasciato. Cioè, avevo scritto delle cose, ma l'ha salvato da qualche parte. Cioè, sono più virtuali, ma non c'è un cambio. Era quello del professore, ma non interessa. No, non c'è. Allora posso farlo.
Non sono accorto. Ok, poi adesso visto
Spagna perché nella mattina ritorno stava che potevano essere tipo PG, i nostri comic, Bitcola per farli vedere e anche Spagna. Perché il problema è che con PyCharm non sono riuscito a mantenere aperti i prompt. Lui fa la simulazione, poi apre il codice e lo chiude. Invece col Python rimangono aperti, quindi adesso quando finché non capiamo come fare. Spostare per fare porca miseria. No, allora lo devo fare. No, adesso sì, adesso conviene aggiornare le informazioni.
Octavio?
Yes. Yes.
Sì. Adesso mi senti.
Just. Do you hear me?
Ottavio?
Sentiamo.
Ottavio?
Yes.
People
Michele?
online, can you hear me? Ah. Okay, you have a problem with the microphone. I don't hear you.
I can hear
Can
you.
somebody tell something?
We can hear you.
I don't hear anything.
We can hear also you, Octavio.
Ah, okay. So the problem is the professor.
Yes, I think so.
Let's see.
Okay. Mm. Perché non sento? I'm Ubuntu on Ubuntu now. Mm. Dov'è l'opzione? Ok. Output volume era 0. Provate a parlare?
Mi senti? Mi senti?
Ok.
Michele?
Provate a parlare?
Adesso stiamo parlando.
Ok, funziona ora.
Ok.
No, it was the HDMI. When you output stuff from Ubuntu, you use
Ah, you are using HDMI. Okay. Good.
Yeah. Okay, let's start. Now, let's go to the lab. The lab is located in the Locosim folder, Locosim, robot control, lab descriptions. And in lab description, you open the PDF L2 joint space control. And this is the what we will do today. The goal of this lab is learning how to design a motion controller in the joint space for a manipulator in free motion at the beginning, and then analyze the advantages or disadvantages of decentralized and centralized approaches, for example, the feedback linearization and inverse dynamics, and then finally implement interaction with the environment using a compliant contact model. So let's start from the beginning. I think I updated the virtual machine with the code and with some software. The software we use today is Spider, and we use that with not PyCharm as IDE for running Python code because we had some issues with the plots. So PyCharm, for some reason, closes the plot after the simulation and it doesn't allow to see them. So unless you didn't do that already, you should pull the last version of the code if you didn't update the virtual machine recently. And
Sorry, Michele, are you sharing your screen? Because we cannot see your screen.
oh, sorry. Yeah, I share the screen and Can you see the screen here? Okay. Can you see the?
Yes, we can
terminal?
see online as well.
Okay. Yeah. So in essence, you should update your code doing a git pull origin master. If it asks you for some config email and user, you can run that 2 commands as is, and that's it. That tells you to run, and then you need to update the sub modules running this command, some module update, and it will update also whatever is in the robot control folder, which is a submodule of the repository of Locosim. Then you, wherever you want, you unless you didn't install Spider, you should install it. So sudo apt install Spider. Okay. They ask you for the password, which is student. I don't understand why it's
We're not seeing the terminal now. We're only seeing your Spider window.
so I cannot share the.
I think that when you share the screen, you can choose to share entire desktop. So you're just choosing to share a window now.
It doesn't allow me to share. No, I'm sharing desktop. You see now?
Okay, now we see the terminal.
So yes. So as I said, git module update. So first git pull origin master. Git module update, and then sudo apt install Spider to install Spider, the other ID we are going to use today, which is equivalent to PyCharm. And then we can run Spider. I already did that, so I just have it here open. And what I do, I open the, so L2 joint space control is the lab with the solutions, and L2 joint space control no solutions is the lab without the solutions. So first, just to be sure, run the lab solution and see that this is happening. So you see the robot moving. Okay. Then we start with the whenever if everything is working. Did you try? Everything is okay. Then you can start to do the exercise of the lab. Of course, if you pull the code, the new code, you need to recompile. So you need to go in the ROS.ws folder and do cat in make install. Yeah, install. Okay. Then this is the UR5 robot. To see the kinematics of this robot, I run the command that is here in the PDF. Okay. Sorry, the PDF is wrong. The command should be this one. No.
You need to source the
Ah.
terminal.
Yeah, you don't have to do that. It's just myself. Um, okay, whatever is doing is this. In essence, you have the sliders. You see that you have here a 6 degrees of freedom robot. You have a shoulder pan joint. Use the sliders. You can move the shoulder lift joint, which is the second joint. Then you have the elbow joint. You have a spherical wrist that has the wrist 1 joint, the wrist 2 joint. Sorry. The wrist 2 joint. And the third joint, which is the wrist 3 joint. That is moving the effector. If you look at another view, you can use your mouse to change the view. You see here, and the wheel of the mouse to zoom in and zoom out. You can see here that you have the end effector, and this is the end effector frame with the X, red, green, Y, blue, Z, RGB. So it's mnemonic, Ross. Okay. Now that we saw the robot, you can see the schematic of the kinematics here with all the joints. These joints have the axis parallel, and this one are the intersecting axis of the wrist 2 joint, wrist 1 joint, and wrist 3 joint, which are located very close together. So no, they are not really intersecting all of them, just 2 of them, these 2. So the first exercise we want to do today is to define a reference for the joints, a reference trajectory, a time varying one, and in specific, we want to define a sinusoidal reference for the second and the fifth joint, which is a shoulder lift and the wrist 2. And the frequency is 1 Hertz and 1.5 Hertz, and the amplitude 0.2 rad and 0.4 rad. And the sign should start from an initial configuration Q0 that is defined in the configuration file x2 conf.py. And the other joints that are not the second and the fifth should be kept fixed at Q0 at the reference configuration, initial configuration, sorry. After 4 seconds, we want to stop the sign and give a constant reference for another 1 second. So in total, we have an experiment that lasts 5 seconds. And remember that we need also to generate consistent references for the velocity and the acceleration, not only for the position. So we start code. The config file I open is x2. And I see here that I have duration of the sign, experiment duration, 5 seconds, sign duration 4 seconds. We have the gains of the PD controller for afterwards. We will implement the PD control law, which is an identity matrix times 300 and an identity matrix for the damping term KD times 30. And we have, in essence, some array that represent the amplitude for all the joints, the frequency for all the joints, and the phase delay. Phase delay we always set to 0, while the amplitude we need to set to we said 0.2 and 0.4, right? And 0.2 is for the second joint, and 0.4 rad for the fifth joint. So first, second, third, fourth, fifth, and sixth joint. This is the sequence. The frequency instead is 1 rad for the second joint and 1.5 rad, so 1 hertz for the second joint and 1.5 hertz for the fifth joint. The initial configuration is given and is this one for the position of the joints, while for the velocity and acceleration is 0. Then we have a flag, external force, that we will use later. So in here, I know that to generate a sign, I want to do the following. QDES. So this is the vector of desired joint variables, the vector of desired joint velocities, and desired joint acceleration. So first we do the desired joint velocity. So we want to start from the Q0, and we add to this a sinusoidal trajectory. To do a sinusoid, we know that we need to multiply the amplitudes times the sine, right? So we use the function multiply that multiplies the coefficient-wise the NumPy array representing the amplitude, which is conf.amp. So we imported the config file x2conf.conf this way, and we call it, rename it as conf. So now the useful thing of doing this is that we can access all the variables that are inside this file as conf.variable, the name of variable. So if we do conf.amp, we will access this amp NumPy array. So we want to multiply the amplitude. So in essence, we want to do this amplitude times sine of 2 times pi times frequency times time, where this is the omega, right? So I previously, since it's convenient, multiply this term here, 2 pi frequency, in here, and I call it 2 pi f. Yes. Yeah. Better? Okay. So now I multiply the amplitude, conf amp, coefficient-wise with sine of 2 pi f times time. And the variable time I already initialized to 0. What is the variable time? Is here. This is initialized to 0. Okay. Then I could also add the phase, the phase here, but we always set to 0, so we don't really need that. But in case you will have. Then to multiply, compute the velocity reference, we need to do the derivative of this because we want to do something consistent. So we doing the derivative of this expression, we get in essence a times 2 times pi times frequency times what? The derivative of the sine, which is cosine, and the argument. Okay, so QDDES, the variable that I already initialized to 0, the derivative of this is a constant, is 0, so won't have any influence, and we need this term. And this one I already pre-computed this way, multiplying the 2 pi f frequency for the amplitude. So I just do np multiply, do the coefficient-wise multiplication of the vector, of this vector times np, cos. This is part of the np package. Cosine of what? Of the argument is the same. okay? Plus the conf phi if we want to have the phase delay. Then for the acceleration is nothing else than repeating, doing the derivative of this to be consistent. So we have a times a, no, sorry, a times minus sign of this times this times what? The derivative of the argument, which is again is this. So in essence, we have I pre-computed this. We have 2 pi frequency times 2 pi frequency times amp, and this is the vector I pre-computed, and I can do qd d des equal to np multiply this, which is this part in essence, times minus np dot sign, because the derivative of a cosine is a minus sign, and the argument. Okay, that's clear. Then we want to, after 4 seconds, setting to a constant. So if time is bigger than equal of conf experiment duration sign that we saw 4 seconds, then what we do is we overwrite qdes equal to q0, qd des stop is I predefine again a 0 NP array with all zeros that for convenience, and also a qdd des equal to 0. Finish. So this is first exercise. We cannot really run because we didn't implement a control law. So let's do first the second exercise, that is implementing the other kind of reference that we want to use, that is useful for our lab. That is a step reference generation. So in this case, we want to generate a minus 0.4 rad plus 0.5 rad step reference at time 2 seconds for the, again, the second and the fifth joint, starting from the initial configuration in Q0, while keeping the other joint constant. So again, in this case, we could do if a step is like this: if time is bigger than 2 seconds, bigger than equal 2 seconds, then so if it's not, else we do the other case. What we have the same as this. So we have the initial configuration and the velocity and acceleration 0. If the time goes beyond 2 seconds, then we want to do the step, and the step is just the configuration Q0 plus an array, an NP array with the first joint, no step, second joint, 0.4 step with a negative sign, third joint, no step for fourth joint, no step. Fifth joint, we set 0.5 rad, and sixth joint, no step. Okay, good. While for the reference for the velocity and acceleration, we take them to 0. So in a instantaneous change of the position variable, and that's it. Okay. Then when the time goes beyond the duration of the experiment, we break the loop. So we have a while true loop, infinite loop, that whenever the time elapses the 5 seconds, just get out of the loop, and what it does is it's doing the plots. So we have the plot joint function that is, for example, plotting the positions of the joints. We can have a plot joint function setting just this string to velocity, plot the velocity, acceleration, and torques. That's it. So the shape of this simulation is very simple. In essence, we define the reference at the beginning, then we compute all the relevant variables that are useful for our controller, that are, for example, the inertia matrix, the Coriolis terms, and the gravity compensation terms. And computing all terms just pre-computes all these quantities, and then you can get them out with the these 3 functions, in essence. So these compute all terms calls the Newton-Euler algorithm for the actual position of the joints and the actual velocity of the joints, and computes all the quantities that are needed for our robot. The inertia, the Coriolis terms, the kinematics, the Jacobians, and then you can retrieve them with these getters, which is this is the inertia matrix, joint space inertia matrix M. These are the bias terms, so the Coriolis and centrifugal effect. These are the gravity terms, so in case you want to extract from the bias terms just the gravity, you can get it, because if you want to use just gravity compensation, we want to use only this. And then we have the end effector position. This is the way end effector position is retrieved in Pinocchio. So this is all this framework use the library Pinocchio, and in essence, what we studied in the direct kinematics, whenever you were composing the homogeneous transforms together, is done in this simple line. So you provide the vector of joint angular position, you provide the name of the frame that you want to compute the forward kinematics. In this case, the name of the frame is the end effector frame, and we define it, the end effector frame here, frame name. So the frame name is called EE link. Okay. Then we need to get the frame ID. This is the way Pinocchio does, but this is just a detail. We put this ID in the frame EE variable, and then we call the function using this ID. And because the frame placement provides us both translation and orientation, we can get the translation part of the homogeneous transform doing dot translation. So this is a 3D vector represent the position of the end effector P. Then we need, for our control laws, also to compute the Jacobian of the end effector. And okay, you don't need these false here, just confusing you the ideas. And to compute the Jacobian, we get the frame Jacobian, robot.frame Jacobian. We provide, because we know that Jacobian is configuration dependent, so we need the joint angular position as input. We provide again the ID of the frame we want to compute the Jacobian to, and this, I'm sorry, is something you need to do if you want the Jacobian in the world frame. Otherwise, you get in the local frame. Otherwise, it's not even an Euclidean Jacobian; it's a spatial Jacobian that because Pinocchio is based on spatial algebra. So this is something you don't know, and just use this string, and it will be everything all right. Then the task. What is the task? The task is to let's forget about this now. We don't need this. We'll see afterwards. Let's see what is the exercise 1.3, which is implement a PD proportional derivative control law. To implement a PD control law, we need to set proportional gain. Sorry, this is an identity matrix times 300, and the derivative gain. We know that this is similar to a stiffness, and this is similar to a damping. And we want to do the same for all the joints. That's why it's an identity matrix. So if we look at our config file, we see here that we set the KP gain as an identity matrix times 300, and the KD gain as an identity matrix times 30. Then we want to use the step reference defined in the previous experiment, in previous assignment, and we want to plot the reference and the actual joint position for all the joints. And we will see that the tracking error is a tracking error is present both during the transient and the steady state. And we want to understand why there is no tracking error in the fifth joint and why there is an overshoot in the second joint. So to implement the PD control law, we look at our lecture that was here on robot control. And the PD control law was defined in slide 21. So KP error in position of the joints plus KD error in velocity, and this is torque. So let's do that. We go to the exercise 1.5, and we set the torque equal to, we access the joint K, I don't remember the name, why doesn't it work? The name of the KP, lowercase, okay. And we do that matrix multiplication. Remember, we need to use the dot function, np dot, and we need to compute the error between the reference joint trajectory and the actual joint trajectory. Okay, the actual joint trajectory are, we will see how to compute them afterwards from the accelerations. And this is the proportional part, and we need also the derivative part. So it's the KD gain dot, because it's a matrix multiplication for an NP array to represent the error, in this case of in velocity, between desired joint velocity and actual joint velocities. Okay. Very good. Once we have computed the torques, what we need to do, you remember the lecture on simulation, we need to compute the dynamics, the forward dynamics. And to implement the forward dynamics, remember we need to isolate the QDD, which are the accelerations. And to isolate the acceleration, we need to do the inverse of the inertial matrix times tau minus the Coriolis and centrifugal terms and gravity terms. So the bias term H is Coriolis, centrifugal, and gravity, contains all of them. So we computed previously tau, we computed previously H, we computed previously M. So we compute the inverse of M. We could even have done this way in my single line. Inverse of M, matrix multiplication, tau minus H. Okay. Now that we have the accelerations, what we do? We need to do a simulator. So we need the states of the rocket. So we need to integrate the accelerations into joint velocities and joint positions. You remember the expression that we define in the forward Euler it was here. No. Probably there's yeah. So was in lecture F1.2, and we want to use, because we know it's a second order system, we can directly integrate position from acceleration, we can get this expression. So first we compute the velocity and the next step, and then the position. So we just implement this, and we see that is exactly what is done here. So this is the velocity at the next step, is the velocity of the previous step plus acceleration times dt, where dt is defined as 1 millisecond. Okay, this is milliseconds. Sorry, it's seconds. So it's you need to measure seconds. So this is 1 millisecond. Then the acceleration is the position is the previous position plus dt times qd plus 1/2 dt squared qd accelerations. Okay, so now we have qd, we have q. The next loop we can recompute the mass matrix and the Coriolis terms and gravity with the updated value of the states. And here are just some log variables. And here we increase the some variables for logging that we use for our plots. So we append at each time, at each loop, we append the value of time, of q to q log, of q dash to q dash log, and so on. And this is the incrementation, the increment of the time variable. And finally, this is publishing to ROS for visualization the values of the joint position and the torques. And once you get out from the loop, you have the plots. So now we can try to run what we've done so far, because we have a simulator implemented, we have the control law implemented, we have reference implemented. So we run the code, and we see that we have the step in the second and in the fifth joint happening. We have the step because it's the we left this this is computed before, and then this is overwriting in essence the previous one. So whenever this is uncommented, you have the step signal. Whenever you comment this, you have the sinusoid signal. And if you look at the plot, we see that we have, this is the first joint, tracking error. The desired one is the red one. The actual one is the blue trajectory. This is the second joint. We see that we did the step only on the of minus 0.4 rad from the Q0 configuration on the second joint, of plus 0.5 rad from the Q0 configuration in the fifth joint, and the other ones are always at 0 reference. So we see here that we have a lot of tracking error. Here you have some errors also due to the gravity. You see there is an offset. Here we have errors due to the inertial coupling. We remember the inertial coupling due to the inertia matrix and the Coriolis effects. And here you have gravity, again an offset applied. And it's interesting to note that this is the pan shoulder joint, so the one that does like this. And you see that there is no offset here because it's perpendicular to gravity. Sorry, the joint motion is not affected by gravity. And so you have only inertial coupling, while this is the shoulder lift that is doing this motion and it's always against gravity. So you have a gravity influence here at the steady state. The elbow joint again is this joint is again suffering from gravity influence, while the wrist joint probably is horizontal, so it's moving this way and it's not affected by gravity and so on. This tracking is very nice because this joint is fifth joint is just moving very little inertias. So if you set the same stiffness, okay, for the first joint and for the last joint, the first joint will have tracking errors because need to carry the weights of all the links, while the last joint has only to carry the weight of the last link, very small inertia. So if for him the stiffness is very high, and you remember if you set increasing the proportional gain a lot, you can reduce the tracking error just increasing the gain. This is a comment that links to whatever we said at the lecture. And we see here that we have a overshoot. Okay, we have an overshoot here, while here we have no overshoot. And this is probably because we set the same gain, the same kx, and the same damping. And if you have different inertias, because one joint has to carry only the last link and the other joint is carrying all the links, this means that you should set different dampings, okay, for all the joints to have the critically damped behavior without overshoot. So probably 30, damping of 30 for this joint achieves the critically damped behavior. We have no overshoot, while a damping of 30 in this joint, because of the bigger inertia, you would require a bigger damp. And 30 is not enough to achieve the critically damped behavior. So let's first see what happens if we increase the gains. So we just set the gains to proportional gain to double. Before we use 600 instead of 300. And again, we want to use the step reference signal. And what we expect is that somehow, if we double the gain, the proportional gain, the tracking error at the steady state is reduced by half. Okay, so let's do that. We increase the gain to 600. Let's see how much was the tracking error. Let's see, this one is around minus 0.5. So we run it again. This is starting in the zero configuration and doing a step on the second joint and on the fifth one. And if we look at the plots, .5 now it was going from -0.7 to -0.5, now it's going around -0.6. So it's just half of the tracking error. Okay, then we can play around with the value of the damping. And we remember that if we increase too much the damping, we can have issues of instabilities because of the discrete implementation of our controller. Our controller is discrete implemented with a sampling time of 1 millisecond. So we cannot increase too much the damping because it has an anticipative effect, the derivative action, and this is anticipative. Sorry, no, forget about that. We cannot increase too much the damping because of the digital implementation. Because digital implementation introduces delays, and so if we increase the damping, for example, beyond 33, and put 34, we will see that the system becomes unstable. Gas just diverges and get to the end stops. Okay, now we will continue to move. There are end stops, okay, implemented in Gazebo that prevent the joints to continually move. But this is an unstable situation, and this is not a number. The acceleration is becoming not a number. So remember, if we reduce the sampling time, we will see that we can allow bigger value of KD. So let's try to reduce the sampling time to 1/3, like 0.1 milliseconds, and you will see that the system is stable for the same value of KD that was making the system unstable before. Now everything is slower because now we reduce the simulation step together with the sampling time. We are not changing the simulation step. We are using the same value for the sampling time and the simulation step. In this case, I told you at the lecture that you should use a lower value for the simulation step. But in this case, we use the same one. But because we decrease to 0.1 millisecond, everything is slow. So at some point, it should start to do the step. But at least you see it's not unstable and everything works. It's just more slow. So in essence, you will be able to increase this value much more, but you will arrive a point in which, or even with this 300 value, it will become unstable. So the value, maximum value of damping you can set depends on the sampling frequency your controller is running. We are closing the loop. So now we go back to the previous values, and we can now try to set a critical damping for all the joints, no? Because in computing the KP gain and the D gain, we didn't consider the inertia. And therefore, we had some underdamped behavior in some joint and some overdamped behavior in other joints. And this means that we were achieving different transient. While recomputing the value of the damping at each control loop according to the configuration, so to the inertia at each configuration, we will always have a critically damped behavior in all the workspace configuration. To do so, we can set inertia, sorry, the damping to this value, proportional gain times the inertia. And in this case, we take, because we are neglecting, we are using the centralized approach. So we are controlling each joint as it has no knowledge of the other joint, of the fact that other joint exists. So we consider, for example, the where is the 1.5? Okay. Sorry, this was going in PD control, which was 1.3, and the PD gain critical damp computation is done here in the 1.5. So we take the KD gain for the first joint, which is joint 0, is the diagonal matrix, and we do 2 square root of the KP gain for the same joint times the inertia. Because we are neglecting the influence of the other joint, we take just the element on the diagonal matrix of the inertia, which is the 0, 0, 1, and that's it. Then we do the same thing for the others. Each one of them will be different. We have 1, 1, 2, 2. Okay. And then we copy this here. I don't know the command to do the column selection, which I like a lot, but we'll simplify this task. Okay, and then we can run. So each loop, this KD gain will be computed and used in the PD control loop, and we expect to achieve a critically damped behavior. So you have the step reference happening, and whenever it comes to plot, we look at the shape of the transient. We see that we have still some inertial coupling, but the transient for the second joint is no longer underdamped, but is critically damped, no overshoot. Okay. Do you have any question? Okay, we are running out of time, so we continue tomorrow with this lab from wherever we left. And tomorrow we will also, if we manage to do in time, to do some exercises for the exam. And so I will stop here. I will put the PDF as well in this folder, the folder of the course. So see you tomorrow.
Bye bye.
Bye bye.